All right, so I got my notes here. We watched the video, which just got flagged by YouTube, so I had to take it back down, so I can't do that one. Yeah, because I included those two videos that we watched that were, can't do that. So, all right, so we were kind of at point 2, I think, which was semiconductor theory. Theory, all right, so we watched the YouTube thing. So we have, we'll say see YouTube. So you can get your YouTube certified mechanic patch. And what did we learn? That silicon, S-I-L-I-C-O, silicon and germanium Michael Jackson's brother, are principal semiconductor materials. Conductor materials. By the way, after watching those videos, do you feel like you have a handle on how the semiconductor works? Or was like, yeah, I don't know what the hell just happened there? A little bit? Okay. So this is kind of what we learned in the video, that semiconductors. I like the name semiconductors. Are they conductors? Semi. Yeah, that's kind of what it is. Have 4 electrons. In the valence shell. See, silicon has 14 total electrons, and they're arranged as 2, 8, and 4. If you remember how we did that, so 2 in the first shell, 8, and then 4 in the last. So there you go, 4. And with silicon, or we could say these two atoms, form bonds easily, and do not easily move one atom, I should say one electron from another, easily, and do not easily move electrons from one atom to the other. Did you catch the Lance Armstrong joke in the one of them?
Yes.
Okay. Is anybody who doesn't know who Lance Armstrong is?
He's the trumpet player, right?
Yes, yeah. That's awesome. How many, Lance Armstrong, how many, famous bike rider, Tour de France, how many did he win? Like all of them?
Like
6.
6. How many before he had cancer?
I was after a lot.
Yeah. He was doing a bunch before.
It was 6 after cancer.
Then he got cancer. Then he went a bunch more.
6 after.
Yeah, he was a pretty awesome dude.
He's lighter weight.
Lighter weight.
He
By-
was
by-
like open like everyone
By
else.
one testicle lighter. And so there was a big controversy about him. Was he doping or not? And then it came out that he was after, of course, he
I just find it smart that they do that. Like,
doping and
blood doping is crazy. Like, they move all your put in blood with oxygen in. That's crazy smart.
germanium has 32 electrons. And that's 2, 8, 18, and 4. I'm not doping, by the way, so. I know. This goes down here because I was talking and not paying attention. That's why I said these 2 atoms when I'm referring to that. So there you go. Now we'll get down to G. Back on track. You can tell I'm not excited about these notes. Trying to figure out another love story for you here. Doping adds impurities, that's what that word is, to the semiconductor. Yeah, to the semiconductor. Sorry, liquid lunch. To the semiconductor material. So here, an element with 5 electrons is added to one side.
What is the word after adds?
Impurities, that's what I said, impurities. Pay attention.
Sorry.
To one side to create an extra electron. So, all right, remember the little smiley face dudes? They're kind of scary. Actually, I like the guy in the big lantern thing. I had a bunch of students who were going to buy me one of those and insist that I wear that while I gave that lecture, and had the 4 little balls on it. And then they doped it, and he had a 5th little one, and so that meant that he had 1 extra electron and was allowed to kind of float around. So that's what we want, one with an extra electron. We'd call this one the negative side. Well, let me put this. This is the negative side, negative side, or often called the N-type. The N-type. Or cathode, which I won't write down. Then we have antimony for germanium, or phosphorus or arsenic for silicone. I don't think we need to worry about that. That just makes it complicated. Then we have an element with 3 electrons is added to one side, to create a hole. But it's often easier to think about that hole as being more of the positive side of things. So I'll write that. This is the positive side. Or the p-type.
When you say create a hole, is that when they made that like red circle?
Yep.
from one
It's like
side?
missing an electron.
Okay.
Then we have the spot where the 2 elements come together, the spot where the 2 elements come together is called a junction. And within that junction, we had what we called the depletion zone. Depletion zone. Almost done here. So electrons flow in the N-type toward the junction, and holes are imagined to flow towards the junction. Imagine to flow toward the junction. But in reality, electrons flow from the junction outwards. We'll put that, but in reality, electrons flow from the junction outward. Flow from the junction outward. All right, let's see if we can make some sense with this little diagram. So here we just have a diode. You guys remember the diode that you messed with, right? It's something that looked like this. There we go. So we had a diode. And the diode is a check valve, right? It only allows electrons to flow one way. And if you think about diodes and how they're drawn and such, you kind of look at it, well, we have an arrow, and the arrow kind of points this way, right? Well, problem with that is this was thought about way back in the day when they thought that things flowed from positive to negative. So that's how I kind of remember it. It's like, yeah, the arrow shows this way, but that's way time ago. Way time ago. So that's what it would look like. That'd be the positive going to the negative. So now I know that it doesn't really flow that way. It goes from the negative to positive. So I know that this is the negative side. That's the positive side. Some people look at it a little different and say, well, I'm not going to worry about how it used to be. I can see this line right here, which is just a negative laying on its straight up and down. So that's the negative. So if you put the negative and the negative together, the thing's going to work. And so if you do it like that, it's going to work. And that's what this drawing is right here. So we have the negative side right here, which flows up. And if we have a negative here, what does the negative do? Does it attract or repel? It repels. So it wants to push all of these negatives, all the electrons this way. And so it gets to this area right here, which is also known as the two names, junction or depletion zone. And what they're representing here, these are all the little holes. And so it's thought of like the holes go to the right. I don't know. I don't really like to think so much. I mean, yes, you have an electron and a hole. Well, in order for the electron to go this way, they got to switch places, right? So that's why the hole is moving this way, but the electron's moving that way. And that's all I really care about, which way the electron's going. So we get over to here, we have a positive, and the positive is going to attract, and so it's going to attract the negative, so it's going to keep pulling it through.
When that hole goes to the other side, does it get filled by another one coming in?
Yeah.
And then it just keeps doing that cycle?
Yeah. Or you can just, it's kind of, it just makes a space, and so the space moves over, so the negative goes here, then there's a space here, and it continues that way, and so it's just going to go down the line. So we got that going on. Well, if we kind of back it up and we look down here, and we have our diode right here, this is what's going on here, so we still got the diode, and of course, this time we've hooked up the negative this way and the positive over here. And is that going to flow? No, and why not? Well, because we got the positive over here, and the positive wants to do what? Attract or repel all the negatives? Attract, so it pulls all of the negatives over here to this side, right? Kind of like this this is like the prison yard here now. No, I shouldn't. You have one gang member is over here. They're all going to be here. All the gang members over here. But it's a band camp prison. So these are all the tuba players over here, and these are all the drummers over here. And so they don't like each other. So they're all in their own corner. So we have the negative over here, which is going to tend to attract the positives, if you want to think of all these as positives. So it pulls them over here. So you have a very wide depletion zone, which is why it isn't going to work. But one thing to remember about diodes and electricity and so much is that's all fine and well if I'm talking about, maybe a couple of 9 volts right there. But if I put 900 volts, guess what's going to happen? It'll probably flow just fine. Or smoke or do something. So that's what we have going on. So as we look into the next, we kind of move forward just a little bit to the next piece of the puzzle, which is going to be transistors. It's just really helpful to keep this this theory in mind, and that's what's going on. So remember, we're going to call this one, we can call it on, right? Or 1. By the way, I was like 2 years ago old when I figured out, you know, all your computers and everything, they have this and this. Well, is that OFF or is that ON? I could never figure it out. And what is this for, that line? Then one day it occurred to me, it's a 1 and a 0. Right, yeah.
I just learned that now.
Okay. So that's a 1 and a 0. They weren't very clear on that, but 1 is then on and zeros are off. So that's. Well, yeah, but I thought it was an O, and I could never remember if it was O for on or O for off, you know? Yeah. Actually, I've learned that a long time ago. All right. Going back to discard. This, where does that leave me? Okay, so now we'll talk about diodes specifically. So we talked a little bit about then the idea of these materials, the silicone, germanium, and whatnot. It's Michael Jackson's brother. What's his actual? It's Jermaine. All right. So like an electrical check valve. And then here, so note the arrow or the triangle shows direction. Shows direction for conventional theory. Or, you could say, the negative mark can be thought, I'll put that negative mark, can be thought of as the negative side, as the negative side for electron flow, for electron theory. Which is to say, in a diode, or if Hannah was here, Dioide. Current will only flow in one direction. Not to be confused with the band. Well, I do what? Go back up? I mean, take it up like that? Okay, when forward biased, electrons flow into the N-type, pass through the junction, and out the P, out the P-type. I know you guys have your masks on, but it's worth it. Come over here. Smell them. That's what a new American smells like. Let's hear it. Yeah! How about that? Let's get that new American smell. How about that, huh?
That's great. Congratulations.
That's a reference to cars, because cars have a nice new car smell. That's, he's going to go home and tell, they said I stink like an American. You know. We all love the new car smell, so. Hey. When a diode is reverse biased, reversed biased, I'll just put electrons cannot flow. Electrons do not flow. I had something else written, but I put a picture over it, so I don't know. Electrons flow, something unable to flow to the junction. Whatever, it's all the same. Let me see. Well, I'll move this up here. An example. Put this here. So diodes have very low resistance in one direction. And show open in the other direction. How much resistance does it have?
I don't know.
You don't know, do you? Okay. However, the indicated resistance with the ohm meter, indicated resistance with an ohm meter is dependent on the input voltage of the meter.
Basically saying what setting you have it on, R1, R100.
Yep. Or the different meter. One meter may use a D cell, another one uses a 9 volt, one uses a AA. It's all going to change. You can't measure the resistance on there. You can only measure the operating resistance. And how would you figure out the operating resistance?
Voltage drop.
Voltage drop. All right. But you can't actually test them. So a digital VOM, volt ohm meter, will measure voltage drops. Will measure voltage drops. So you actually have on some meters a diode checker. So you can put it on a diode checker and it will measure the voltage drop and tell you what it is. So a silicone will show about 0.6 volt drop in forward bias, and zero, I'll put that forward bias, and 0 volt in reverse, REV bias. Germanium will show about 0.3, will show about 0.3.
Is that the same forward bias?
Yeah. So we don't just have one type of diode, of course, that would be too easy. We have many different types of diodes. You have already seen some of them.
Can you bring it down just a little bit?
Yeah. Could you write a little faster? Maybe it'll just look like I wrote it then. Right there?
No, it's the same thing.
Oh, zero. Yeah.
Different types of diodes. All right, what do we got? Got your LED, which stands for Really?
Yeah, we could go.
Okay.
That was back in week 2, I don't remember that.
Light emitting diode.
Is this E or F?
F. Oh, I remember I skipped one, so I moved everything up. So that would be E now, huh? I'll have to keep remembering that. My F is just it was the PowerPoint thing that I went over. I'll write this because it's kind of interesting. So, photons are released when electrons meet holes in the junction. Then if depending on the material, different colors can be produced. Different colors can be reduced. Let's see. Who has airplanes? Harry has some, and then you have the club. Either one of you guys got LED lights on your plane? Now, it's not for a lack of want. What does a set of LED landing lights cost for our airplane? About $1,000 bucks?
Oh my gosh, yeah, something like that. For one bulb, it's like, what the heck?
800, 900 bucks.
LEDs are crazy expensive.
No. If you have an experimental, that exact same bulb is about $30.
Really?
Yes.
I have LED
So
push
it's just
buttons.
because it's aircraft grade.
Yep. What's that? What's that?
They have LED push buttons. You just push,
Nice.
and they're like $800.
Oh,
They're
man.
insane. They're square like this big. $800. Big phone.
Wow.
Insane.
However, I will say this, whenever I worked on airplanes, we had the incandescent bulbs as landing lights, and those busted like 10 times the rate, and I never, ever, ever had to replace the LED lights that we use for anti-collision lights.
That is true. Yeah.
LEDs are a lot more reliable.
Yeah. So when I was flying with Phil at night, he's like, that's the first thing he did is, well, you got LEDs or you got incandescent? I said incandescent. He's like, oh, it's during the day one time. It's like, I'll leave them off. Because, in my plane, flying with the incandescent on, it's going to do two things. One, it's going to suck power out of, alternator's got to work harder to keep that going. So that's bad. So it's going to use more fuel. And the next thing is because of the current draw, the switches get hot. There's actually a service bulletin on Cessnas. We were supposed to replace the landing light switch after so many hours.
It gets so hot.
Just wear out. Probably, from the heat. Voltage drop. I thought this is cool. Voltage. Never tried it. Should. Is different for each color.
Oh, really?
That's what it says. I keep meaning to try it, but I get to this point, I'm like, nobody's actually doing this.
So you're saying for a purple LED, it's got a different voltage drop than a blue LED?
Yes, but a purple one and a violet one have the same voltage drop.
Yeah.
As would a cayenne and a blue,
Yeah.
or a magenta and a red. They're, I don't know. Okay, laser diodes. I have said laser diodes. Where would you find a laser diode?
Oh.
Yeah, it's something on your
Well, it's similar to an LED. I don't know how old is this. I don't know what kind of diode. I don't know what they actually use in a laser. I don't think they use diodes. It's actually a laser. So where would you find a laser diode then? Like this?
your mouse.
Yeah.
Oh, mouse. That might be a good one. Optical drives. Back in my day, we had records, but they were small, and you would put them in your car, and if you looked in there, there was a little laser that would go down and read the record, known as a CD.
Wow. Back in the day.
Back in the day. So optical drives use those. We have photodiodes.
Back in my day, we used to use cassettes.
Photodiodes. This is where they're set up so the N and P junction is designed to sense light. So put NP junction. Junction is designed to sense light. Is designed to sense light. When light reaches the material, DC voltage is produced. Where would I find these?
Your car.
Where?
On the dash.
Dash, I suppose so.
For like your headlights.
Yeah, for changing headlights.
Your cell phone?
Let me think.
Yeah, your cell phone for the auto brightness.
Solar panels, light sensors.
Windshield wipers. For the new cars.
Oh yeah, I might have that in my window. Light sensors. You might see them in, let's throw this one out there, smoke detectors. So you might see it there, like a lack of a light could trip something. Because there's photo sensors and there's ion sensors. There's different types of smoke detectors. All right, then there's this one. It's the Schottky diodes. Oops, spell it right. S-C-H. S-C-H-O-T-T-K-Y. That's like Schottky. Schottky. These are the new and improved, sort of. Have lower voltage drops, which makes them more efficient. And they have faster switching speeds. Faster switching speeds. Disadvantage. The diode has a larger reverse leakage. Has a larger reverse leakage. Remember when they came out with chips that had this stuff called olean in them? Potato chips. They were like no fat. Remember those? What was the warning on the bag? It caused a reverse leakage. You'd get the butt leakage. Yeah, it's a bag right on there. Warning: excessive consumption of these chips may cause anal leakage. That's why you don't. Yeah. I don't feel good. I just leaked a little. All right, we good? How far are we? All right, I'm moving it. Here we go. In 3, 2, 1.
Oh boy.
Who's gonna? All right. Last one. The Zener Diode. I think this one's on your Q&As. Zener, Zener Diode. These are kind of more common. Well, not that the LEDs are and stuff, but I do see them. Allows current to flow in the forward bias. Well, that's good. Allows current to flow in forward bias, which is what a diode is supposed to do. Allows current to flow in forward direction, the same manner as irregular, so that's same as everything. But it also permits current to flow in reverse direction when the voltage is above a certain value. Certain value. That's known as the breakdown voltage. Known as the breakdown.
Couldn't that technically be for all of them? Put enough voltage in reverse, it can still work?
Yes, but this one's specific. That ruins it. Now it's like, okay, so you got to put a new one in.
Okay.
This one doesn't break it.
Okay.
It's designed to do that. So one of the, I thought I had like a list here. Let me see. So where you would see something like that would be in like a voltage regulator. If the voltage gives above a certain point, that's bad for the aircraft. Does it want it to be that way? So you can actually then take that extra voltage and you can send it a different way around into a voltage regulator. Let me see. I thought I had the schematic for that one. I'm pretty sure it is, I won't lie to you, I think. It's got a Z to it. Oh, it's like this. There it is, right? Okay, yeah. So it's going to look like that. So when you see that little negative, that's a Zener diode. I think I put it the right way. Did I put it the right way?
That's good.
Yeah, I think that's the way it goes. So a Zener diode. All right, those are your diodes. Let's talk about, oops, that's not G. What's before them? That'd be F, huh? F. All right, considerations. Things to know about diodes. 1, diodes get hot. Not terribly bad, not like an incandescent light or something, but there is heat. Why is there heat? Resistance. How do you know there's resistance?
Voltage drop.
Because you got a voltage drop. All right. And are often attached to heat sinks. So we look at alternators. We're going to look at alternators that have pretty large diodes in there because they're going to be used to make DC current out of AC. And they're going to get kind of hot in there because it's a lot of current flowing through them. And so they have very large heat sinks. And a heat sink is something that is attached to a diode that allows the heat to dissipate out of the diode into another piece of metal, which then can be air cooled. So that's what a heat sink. In the alternator, or any diodes, they can be used in rectifiers. You'll see them there. Are used in rectifiers. We talked about rectifiers when we talked about, what were we talking about? Meters. That was it. And what do rectifiers do? Oops, rectifiers. Rectifiers allow AC to be easily converted to DC. There we go. That's what we looked at before. Can you remember that? All right. So from negative to positive, electrons are going to flow this way. They're going to get to this junction. Got the arrows to cheat with, but you can't go down here because that would be reverse bias. So it's got to go this way. It's going to get to this junction. Can't go that way because it would be reverse bias. So it's going to come down, go through the DC load this way, come back to this junction. So now we've been following the negatives, right?
Yeah.
Okay, now I'm going to get to here and go, well, negative and negative. Well, why can't it go this way? And that becomes that theory, which one is more negative? So it is more, so we're on the positive side now, sorry. So now we come back to the positive side. So we're on the positive side. So you can say it this way, positive here, well, Neither one should work, right? So why is it going to go this way? I mean, you'd think the diode would be turned around, but,
More positive.
huh?
More positive.
More positive, right, because you have to look at it from this way. So this is the more positive, and that's the more negative side. So even though I've entered into the positive side of the circuit, right, I get to this and go, wait a minute, this side over here is more positive than this side. So this makes that positive and that's the negative, because we're going to have a voltage drop. If you think about it another way, if I wanted to measure the resistance of this particular diode, right, and I have my Simpson meter, which side would I put the positive lead on? Upside or downside? So I'd have to put my positive lead there and my negative lead there to get any sort of reading on a voltmeter. So you go, got it. That's the positive side. That's the negative side. If I reverse those, you wouldn't get anything out of your Simpson meter. So, okay, so that hopefully makes sense. So this is the more negative side. So it comes back and around and there it goes. So and we can run the same diagram through here. But what's happened here is the positive is on this side and it was positive on that side. So the positive and negative have switched, which AC does, and it's just going to run through it backwards. And the net result is that current flows that way, no matter what, through the load, so it makes it a DC load. So we're going to see more of that when we talk about alternators. All right. Transistors. So now that you understand that, what else do I have on here? We can talk about transistors. There we go, transistors. Right there. So when you look at them schematically, back to what week 2 stuff, the only difference really is this little circle right there. I'm sorry, am I boring you? All right, so we've got, that's the only difference when you look at them. So this one is not pointed in. It's an NPN. And this one is pointed in. Pointy. It's a PNP. Right? It's easier to start at the top one. I don't know what they had the bottom. Huh?
Pointed in place?
Pointed in place. Sure. Yeah. So the not pointed in is what I always start with and just go down to that one. But anyway, that's how I remember it. So not pointed in. There you go. It's pointed out. So if I look at this one, I go not pointed in. No, that's not right. So, but you'll notice that the base otherwise is the same. The arrow's on the emitter and the collector's right there. What else can I say? Okay, the base is important because that is the control switch. And so what this is, if you just take a look at it very simply, and as they pointed out in the movie, the little thing, it's really just a switch, right? And the base is kind of like your switch input. And then it's like, okay, well, which way is this going to flow? Well, one of the ways I go back to is thinking, okay, if we think about it in conventional theory, then it would make sense that, say it's going to flow this way. Collect it here and then emits out. And I go, okay, that works for me. I was trying to think there was a way that I don't remember it right now. It'll come to me. How it made sense to me going the backwards, what collected and what emitted. You can switch it around. I'll have to think about that one. But I had a thing at one point. What's that?
It'll come to you when you don't want it.
Probably on the way home. Then I'll tell you tomorrow. Okay. So that would be transistors. All right, so we have 2 types. 2 types. One, you had the NPN, or the not pointed in version. Base is a P-type. So the base is P-type. Another way of doing that, so if I want to look at a transistor, I can just draw it out like this and say it's an NPN. And I would say the base is p-type, so that's the base. The base is p-type. And that would make the collector and the emitter n-types. Are n-type. And then the next one would be, what should I do? These should have been moved in a little bit. So that would have been actually 0.1 and 0.2. Then I can make this one II, and then I could say PNP, which is the opposite. And then I could just say 1. So we have PNP. P and P, so that would make the base is what type? N type. And the collector and emitter are P type. And to be honest with you, I don't know who selects one, why somebody says, well, this should be an NPN, or this one needs to be a PNP. I guess it would just depend upon the junction that you have coming at it and how they designed it out. When you get to that point, like, well, now I got a positive here, so that's going to be an NPN if you're on the base, or if it's a negative on the base, then you're going to do the PNP. Otherwise, they're going to work the same. Let's see. That was A, B. We can put this transistor. Is like a switch, or solenoid. I know in they're used for amplifiers. We don't really have to look at so much how it's going to work as an amplifier. We're only asked to pretty much look at it more as a switch or a solenoid. So I will leave it right there and let you have a break.